is, of course, my great pleasure to welcome Professor Shogato Bose from University College London as our speaker for today and in the RRI Quantum Science and Technology webinar series. Just a short introduction to Professor Bose's, achievements and his, educational background. So Professor Bose is, of course, at University College London. He has been there since 2003 in various capacities. He is currently, of course, a full professor in physics and astronomy. And he did his PhD in physics under the supervision of Professor Sir Peter Knight from Imperial College London, and on entanglement, manipulations, and applications. And since then, he has been a junior research fellow at St. John's College, Oxford, as well as a postdoctoral scholar at California Institute of Technology. I have a short CV here, but the number of fellowships and awards is definitely not short. So what I will do is name 2 or 3 just representative ones. He of course has the Maxwell Medal and Prize from 2008, the Royal Society Wolfson Research Merit Award between 2007 and 2012. And then one of the things that is an India connection is he is a Satish Dhawan Chair, which is an endowed visiting chair at the Indian Institute of Science, which is a neighboring institute in Bangalore. Professor Bose has a history of, having successfully guided several students. He has taken a very active part in all sorts of academic activities at UCL, which makes it very difficult to get email responses from him. On a personal note, Shogato is one of the most, one of the easiest people to talk to, I would say. So I have known him now for several years. He's a highly accomplished individual, but then when you talk to him, he comes across as one of the most humble people I ever know. So combination of humility and accomplishment, I think very few such examples that I know of. So on that note, Shogato, the floor is yours. And of course, you're going to talk to us today about quantum information and spin chains, right? So please.
Thank you, Urvashi. Thank you for the very nice invitation. Right, so I gave a very broad topic, and of course, there's a lot to say in this. And in this area, a lot of people have worked, not just work coming from our group. But my presentation will be linked to mostly to the work that we have done, just because I'm better aware and better able to describe that, right? And again, it's a very broad area from the title, so I will be giving mostly an overview style talk of various things one may do here in this regard. And hopefully, if you want more details, that can be found elsewhere, or I can discuss during the question sessions and things like that. Okay, am I audible properly?
Absolutely, absolutely, yeah.
Okay. Okay, so so the talk is kind of in 2 parts. Okay, so I'm going to look at 2 aspects. So first of all, spin chains themselves can have quantum information applications, such that they could be a quantum channel, they could be a source of entanglement, okay, they could lead to have gates and perhaps even a rudimentary algorithm or such, yeah. So those are some things I'll try to exemplify. On the other side, on the flip side, there's also an application of quantum information measures to spin chains. Okay, so I would say that is quantum information given to a spin chain application, right? So there one can compute various things such as entanglement and other quantum information, inspired measures, and see whether they help us understanding something about the system. Okay. Spin chains are kind of ubiquitous. Okay, I'm going to, historically, of course, they were used to model magnets, right? But they can model everything, including, up to quantum field theory in the continuum limit. I'm going to use the word spin chain both a bit broadly and narrowly in the same, so it's kind of loosely, okay? So first of all, I'm going to, everything I'm saying in this talk is just considering spin half systems or qubits, okay? And at times, only probably just at one time, I'll be considering graphs. So just some like a more expanded definition. So the main thing I'll be using the word spin chain as systems of permanently coupled qubits. Okay, so the interactions are frozen in time. Okay, and maybe very few, some interactions here and there are controlled. And one aspect will be what we can do with such systems. So even if you want to control one or two interactions here and there, say to input quantum information to a system or take it out from a system, you have to have some degree of control, and this interface is not always well developed. So in some sense, what I'll be talking about applies more to simulated quantum spin chains in say various quantum simulators rather than actual magnets and stuff. But that is also interesting to pursue what one can do with real physical systems. Okay. Now in this cartoon here, these bonds I have drawn shows interactions like nearest neighbor, next nearest neighbor, next to next nearest neighbor, like that in a loose sense of the word. Okay. Now, right. So the first application, and historically, this is the earliest kind of thing I started working on. So this is how I got into spin chains, and this has been some things from a long time ago, is how one can actually use spin chains as quantum channels between quantum registers. Okay, we know that there are various reasons for which quantum registers, individual ones themselves, cannot be scaled to large sizes. And to make a more powerful quantum computer, you will need to connect them. This is one of the crucial issues in scaling quantum computing. And usually one envisages to use photons, so interface qubits, whatever they are, atomic or spin or superconducting, whatsoever. You have to kind of interface them with photons in some way, some type of photon or other, yeah? And then jointly measure them or send them from one race to another. Or you think of physically moving qubits as people really physically move ions. Okay, so it might be considering an option where you do not physically move qubits at all. Okay, so you connect up registers with a permanently coupled array of qubits. Okay, in other words, a spin chain. Okay, so this, you can use the same type of qubits as you are using, okay, to build your registers, and you have a connection. Okay, and then the idea is you will think of it exactly as people think of a quantum channel. Okay, so like say an optical fiber transmitting photons. So the transmission will not be perfect necessarily, but then you can use quantum information techniques such as entanglement distillation, okay, which is a kind of variant of quantum error correction. So you can do multiple transmissions and then make your entangled state of a much higher, a better quality entangled state. Then you can use quantum teleportation to connect such quantum registers. Okay. Now, there is also another important fact that you may, and this is an interesting point which was brought up by my first PhD student at UCL, Daniel Burgard, is that even when you have the capability of enough control, you may need regions of low control in something like a quantum computer, because we have our macroscopic controls and they can hone into only as much number of qubits. And you may deliberately want to space them apart and have some regions with just the connection. Okay, and if they are doing just the connection, then you just don't have so many control electrodes to put in to have individual control over them, to really use them to do individual like swap gates or something to move around quantum information. So it would be nice if you can really use things such as so it's a fully connected permanently coupled system, and use, so then that becomes a spin chain essentially. So this is kind of a spin chain which we artificially make inside a quantum computer, just because we do not necessarily want to have to control all the parts. Okay, maybe it's just difficult. Okay, and then if you can still have the connection, then it's part of one quantum computer. Okay.
Excuse me, Shobhita,
Yeah.
is it
Yeah.
okay for people to ask questions during the seminar, or should they wait till the end?
It's possible. Yeah, short questions I may answer now, and then
okay. Yeah, something that people can then keep in mind. Yes.
Yeah. Though I'm unable to see chats and things, so it's possible. It's best.
No,
for
I will
people.
read it out if indeed there is some pressing question in the chat. Yeah.
Yes. So the earliest model I considered is the simplest one can think of. Okay, so you have fully symmetric interactions between two qubits, which is nothing but the Heisenberg Hamiltonian. Okay, it's just a swap, yeah, interaction between the two qubits. So it's fully symmetric in the Pauli matrices, and those have been used historically to model ferromagnets. Okay, Heisenberg ferromagnets. So typically a ground state is something in which all spins are aligned, okay? And then you can imagine putting a quantum state at one end of the chain, and then it flows, yeah, through the different magnons as a quantum superposition of different magnons like a wave, and it reaches the other end, okay? And more concretely, what will happen in this particular case is that one of the situations when you put a down spin is going to become a non-evolving state, because as a whole, that is the all down is still an eigenstate of the Hamiltonian, while a single spin at one end is like a quantum walker, okay, walking through the chain, okay, which will disperse and walk and reach the other end with some amplitude, okay, an amplitude of transfer of an excitation from the first site to the nth site, okay. And of course, there are many interferences involved in this transmission. So what happens? So if you check this out, you will see that for some numbers like 4 and 8, there's almost near perfect transfer of information. So you don't have to do anything. These are equally coupled qubits. Chains of 4 and chains of 8 will nearly perfectly transfer the information given enough time. Okay. So there's an optimal time at which you have to stop the interaction of the last one, which has received the state. And there's, of course, time equal to 0, where you have to couple in the first qubit to the chain. Okay, that's the scenario under which it works. And then we can see that you can do useful quantum state transfer, okay, which means that better than 2/3 fidelity. 2/3 fidelity is a kind of transfer you do just by calling someone up, okay, on a classical phone. So when you reach above that, it's kind of useful. Okay.
Can I ask a short question?
Yeah.
So what makes 4 and 8 special?
Interferences. Yeah. So some kinds of constructive interferences must be happening at some special time. You see. So, I mean, of course, these are cosines of, 2 pi by capital N and various multiples of this at which the phases evolve. So, yeah, it's some kind of constructive.
And then some damping takes over, which doesn't make 12 also near perfect?
We have, of course, in this case, we just waited for a finite long time. Okay. So later on, something which is not here, later on, people have proven that if you have some particular numbers, then there are certain values at which you will come arbitrarily close to 1. Okay. And multiples of 4 would fall on that in that category, but the time is not guaranteed. So 12 might come significantly higher, okay, if you given enough time. Okay.
Thanks.
So there's a paper by Simone Severini and others, which investigates those things. Yeah. So not considering what time. Okay. Now, now the thing is, of course, we have to do experiments in a finite time. Okay, of course, otherwise decoherence will come up, and then the transfer due to this dispersion is not necessarily good. Yeah, it's a bit like a photon being absorbed in a channel, having some amplitude of being absorbed. Okay, so what one then can use is this thing called dual rail encoding. Okay, so you have two parallel spin chains, and you encode the information as like up down and down up kind of way. Okay, and then you let the information go, and at the end and receiving end, you can also check whether an excitation has arrived. Okay, so you can check the parity of the qubits, whether it's 1 0 0 1 and not something like 0 0, okay, or 1 1, but you do not need to check about which specific case it is. So you do not destroy the quantum information. So with some probability, you'll be receiving the quantum state perfectly. Okay? So all we have done is, by this dual rail encoding, is we have converted the amplitude of partially reaching partial, damped quantum amplitude to actually a probability of the state reaching perfectly or not yet reaching. Okay, so when you find 0 0 here, it's not reached yet, and there's no chance of 1 1 under ideal conditions. Now, people have also optimized such couplings. Okay, of course, the optimization of couplings took place in a slightly different scenario, not this kind of symmetric coupling, so not the Heisenberg spin chains that I was talking about, but if you use XY spin chains, so it is something without the ZZ interaction term. Okay, yeah, it's XX plus YY. Okay, those spin chains. If you first of all, those spin chains have this property that they are like free fermions. So fermions do not seeing each other, just hopping along the chain. Yeah, it's mappable to that. And additionally, if you make the couplings particularly engineered so that the whole system has kind of an integer spectrum, say for example becomes like a particle in a box, then combination of these two can give really perfect transfer even using one spin chain. Okay, I mean, of course, this is very hard. This is not very physical to make these kind of engineered couplings. But what happens is, just like a particle in a box, you can see if you have alternate states of opposite parity and you have integer spectrum, you can show there will always be mirror reversals. So whatever is in the left, that wave function will reconstruct in the right after a certain time. So this mirror reversion, along with the fact that the particles are just going independently, not interacting, scattering from each other, just you can make perfect transfer of states. Okay. Now, what can one? So as I told, during this perfect transfer, these things are mappable to free fermions. Okay, so the interesting question is, so immediately, since we know free fermions, there's a curiosity that we know when two fermions exchange, there's a -1 sign. Whether that can be effectively used for a 2-qubit gate. Okay, so that's one important question. So what we have in mind is an array. One can consider it an array of qubits held somewhere, say in individual traps. And then there will be a bus coming from the top. It could be like an optical lattice or something like that, 1D, which will be at the top of this array. And whether that can implement these kinds of gates. Okay. This is just the mapping. It's a very well-known mapping called Jordan-Wigner fermionization, which converts, spins to fermions. So every up spin is like a presence of a fermion, down spin is like empty site. Okay. Now, what happens due to this kind of XY chain is, the fermions are, during this mirror inversion, are crossing each other. Okay, so if they cross, we know they get a minus sign. Okay. So this then can be used to make a quantum gate. Okay, so if you have say empty, then of course no sign change, and if you have one fermion in each end, which are like a state 1 0 or 0 1 between the endmost quantum bits of the chain. Okay, those will also not have sign change. But when you have one spin up here and one spin up here, rest all down, okay, means that there are two fermions, and when they exchange, you have a -1 sign. And that is all you need for an entangling quantum gate. Okay, this is a control, this is similar to a control phase gate, except that 0, 1 and 1, 0 got swapped as well. Okay, but that is easily taken into consideration. It is still an entangling state and perfect for universal quantum computation. Okay, so one would envisage a system like these trapped qubits in an array, which are not able to interact at a distance. Okay, they can only interact with their neighbors. Okay, then they can be all made well separated to not interact with anyone, and then only you bring in a bus and push with some, say, optical force the atoms closer to the lattice to have a interaction. Okay, and then you can do these kinds of gates. Okay, XY interaction, of course, is more difficult than Heisenberg interaction, but one can do them with appropriate things. Okay, one also has to block the rest of the bus and stuff like that. Okay, so this is one way one can do universal quantum computation in an array of very distant non-interacting qubits by only using a bus on the top from whenever you want, actually. Yeah. Now, this can, of course, happen with engineered chains, but can also happen with kind of non-engineered chains with quite high fidelity. But something much more wondrous happens when you do use engineered chains. You can do something very interesting, which we found out, for example, you can start with a state which is up, down, up, down, up, down, okay? And then two things: A, this initial configuration, and B, the fact that there is this perfect transfer in this mirror inverting chains, okay? And 3, that they are free fermions. These 3 things together, okay? The initial condition is also very important because a fermion cannot sit on top of another fermion, so that is something also important. So these 3 things together, what they do is that at a time which is half the time in which the system would perfectly mirror revert, what happens, so I've shown a chain with an odd number of sides here, is that you have perfect entangled states, Bell states generated, okay, between the ends. Okay, so this is like a source of entanglement.
There's a question in the chat. Can I read that out to you? Yeah, it's from Prasanna. Yeah. So is it possible to make some general comments on how robust is the state transfer in the spin chain models to disorder? For instance, in the couplings that may be inevitable in implementations.
That's true. That's a very good question. Okay, so it is comparatively more robust to exchange coupling disorders. Okay, of course, it's not completely. I mean, disorders would. So we don't have the graphs here, but we have studied disorder. Of course, spoils the thing, but it's comparatively much more robust to exchange coupling disorders compared to random magnetic field disorders. Okay, so if the local energies are changing, then it is quite susceptible. Okay, I mean, after XY chain is completely susceptible because you immediately have Anderson localization. Okay, but with finite sizes you can do something. But when you have exchange coupling, sufficient fluctuations can be tolerated. Yes. Now, of course, this means also you have to take care that those fluctuations are not there, those disorders are not there. So in some sense, we will, that's why I'm advocating you do these kind of things more with the quantum simulators and stuff, where you have arrays rather than very natural systems where you may have disorders inbuilt. Yeah. So exact quantitatively, I cannot tell you immediately, but for various sizes, there are graphs we have made. Maybe we can talk offline, yeah, about that. Okay, it's an important question, definitely. Okay, now as I say, it's at half the time of reaching somewhere. Okay, you have these kind of rainbow-like states. Okay, and then again at the time at which things would have perfectly transferred by mirror inversion, you know what will happen. The nil state will go back to the nil state. Okay, so interestingly, what's happening here is that every excitation is somehow reaching with half amplitude to its partner on the other side at half the time, though it is not a system with a direct super exchange, right? It's really going through the chain, okay? But the initial condition makes it forbidden to move in certain places, and then the free fermions reach exactly this kind of situation. So again, at 3t star by 2, there will be this Bell state. So it's like perfect oscillation. If you set up the system however long with XY couplings, so free fermions, but with engineering, you would have this oscillation between zero entanglement to maximal entanglement between the left and the right, because there's exactly Bell pairs between each, which is like the whole volume is entangled with this volume. So this is a volume law entangled state you can reach from something which is a disentangled state, and this will exactly oscillate. Okay. Now we go to another kind of application, which is that can we do a bit more things. So we have shown that quantum gates are possible. It is possible for this spin chain to be a source of entangled pairs, okay, which we can probably use for something. But can we do more, okay? Can we do some interesting quantum gates, okay, with a connected set of spins? And one interesting challenge is whether we could do things like 3-qubit gates. Okay, 3-qubit gates typically, if you want to do them with a constant Hamiltonian, require 3-qubit interactions, okay, like these Fredkin and Toffoli gates, okay. But what we found is that with some ancillary qubits, which act like a hidden layer of qubits, which are never really accessed, okay, and you just input and output in a given subsystem, you can do this kind of higher number of qubit gates, okay. There's a certain time in which the input register decouples from these ancillary ones, and at that time the gate is completed, okay. And this is an example we came up with. So you see the couplings are very, you know, not very natural. So you have ZZ couplings between 4 qubits and XX coupling between 2 particular of them. Okay, so just is the qubit X and qubit X and the qubit Z, qubit Z. And then you can have very high fidelity gates. Okay, but the couplings came out to be very, you know, not very intuitive and strange, okay, but you can do with those things, okay. But what is the idea of being able to do quantum computation with such a thing is that you put together a few kinds of things. So you have a gate network doing, for example, this Toffoli, or if we manage to do, we haven't managed to do much higher order versions of this, and say a gate network do something else. And this we call it gate network, but it's just like a qubit network, permanently coupled qubits, okay. So we start the interaction at a certain time, and then we switch off the interaction at a certain time, and the gate happens due to the unitary evolution, okay. And then you have some kind of a memory register from which some quantum buses would take it to either this or to that, a specific number of qubits. And in general, you need just 2 distinct enough gates to do universal quantum computation. For example, with Toffoli, we know that Toffoli and just a Hadamard operation suffices, okay. You might build larger multi-qubit gates to easier process and just use them sparingly, and one could do quantum computation. Okay. Now, can you do more ambitious tasks with these things like spin chains? Okay, so so one of the important tasks is to find an unknown marked element, okay, which was the quantum search proposed by Grover a long time ago. And then later on, Andrew Childs and others mapped this kind of problem to a spatial search. Okay, so if you have one site in a given collection of qubits as a marked element, the question is, can you search for it? Okay, and marked by, say, a different energy. Okay, and it is known that the quantum walk, okay, so classically you would have to, if you take a stochastic process like a classical walk, you have to search at least order of n to reach, but quantum mechanically, because you walk in superposition in square root of n times, you can find this out, okay. Only caveat is that you have to be walked from every side to every side. So it's what we call a fully connected graph. So the algorithm works perfectly when you have a fully connected quantum graph, okay. right? Now, what we investigated recently last year is that, so this is work by Dylan, who is, I think, in the audience, is suppose you have, these XY couplings, which are really like hopping couplings, okay, of free fermions, okay? But at the same time, we are considering a graph here, so it's good not to think of free fermions here. We think of hopping couplings of excitations, okay? And the couplings are, say, long range, okay? So they fall off as a power law, okay? So we wanted to see, so this is more realistic than the whole arbitrary long range coupling, okay? That you can have a coupling which falls off with distance, okay? So can they do the job? Can they give a speed up in quantum search is the question, okay? And indeed, we found that the answer is yes, okay? So first of all, so this fall off coefficient alpha, if this was 0, that would be really a fully connected graph, which we know gives the speed up. Now, if this alpha is very high, we know it's just a nearest neighbor coupling, and that people have shown that in dimension 1, you cannot have any speed up due to a quantum walk, okay? So the question arises for up to what alpha can you do the thing, okay? So this was found by so this has nice, easy to solve, because you see the interaction is falling off with the distance in a very symmetric manner, okay? So again, Fourier transforms are eigenstates, just as a nearest neighbor case. So this is a big advantage here. And you can find all the eigenvalues of the problem. And then there are certain things you have to compute, okay? So this minimum gap between the ground state and the first excited state is a relevant parameter. And with what fidelity you can reach is also related to that. Those are related to some quantities you calculate from these eigenvalues, okay? So this is what they did. And what we find is that up to alpha equal to 1.5, essentially you can have, with the spin chain with long distance interactions falling as 1 by r to the power 1.5, you can still have this advantage of quantum search. Okay, so you can still hit the right solution, the site marked with different energy with square root of time, okay, compared to searching classically. Okay. So this is more or less everything that I'll speak about regarding the application. So on one side of the talk, okay. So one side of the talk is now over, which is the application of spin chains in quantum information. Okay, of course, this is an exemplification. There are more things we have also done, others have also done, but this is what I restrict myself now to. And now I'll move to the other side, that what can quantum information measures tell us about, if you apply them to spin chains, can we gain something out of it? Okay, so this is not as constructive. This is like more like exploring. You apply a measure and see what comes out and whether that is interesting. Okay. So Urvashi, I would just like to time, am I half the time or am I over half the time?
I think you're just about at half the time. Yeah.
Just about half the
plus
time.
2 minutes, I would say. Yeah.
Okay. No, that is fine then. Okay. And in the chat, there might be one more question. There's showing like 2, so I don't know whether.
No, that is
okay.
Thanking
no,
you for your
proceed.
answer
Okay.
to the first question.
I see.
Yeah.
So, okay. So what we now we see so we want to apply. So the natural thing to apply when we think of quantum information and spin chains is measures of entanglement. Okay, and historically this is what people have started to apply since the earliest measure was available. Okay, so as soon as Wooters's measure of concurrence was available, for example, then we applied this to measure entanglement of 2 individual spins, and many people have looked at entanglement of 2 individual spins for various kinds of systems. Unfortunately, this does not give that much really indication of the true amount of entanglement in a spin chain. You see, because entanglement is a very monogamous quantity, and then the closest spins are most interacting. So when they're quite entangled, there's hardly any entanglement with the next nearest neighbor, let alone farther ones. Okay, so what happens in the end is that you end up with almost very little information from computing this kind of entanglement, and not very useful either, because they are only very nearest. Yeah, so to useful entanglement, you kind of need them to be separated. Then the thing most widely studied, particularly from the more mainstream condensed matter community historically, and also quantum field theory, is really the entanglement of two blocks, okay? A left block and a right block, okay? This is much more informative of the net entanglement in the system, like everything with everything. At the same time, it doesn't tell you how much entanglement is there between, say, a subpart, like this bottom picture, and another subpart, okay? So this is also could be a quantity of interest, especially if you think of the kind of application I was talking before, okay? That we were wanting to distribute quantum chain as a channel. So one, if it has entanglement between two well-separated parts, perhaps you can utilize it for something, or that has a physical interpretation, that it is really the entanglement between this, and how much is there is a question. So that has to be investigated with some mixed state entanglement measure. This is called the negativity. Okay, so you have some separation X, and then you have some blocks of length, certain length, and we want to investigate the measure. Okay, now. So when we have such non-complementary blocks, one important thing is that the von Neumann entropy itself does not suffice, because if you compute the von Neumann entropy of A and B, that gives its entanglement with C, but not entanglement between A and B. Okay. To get the entanglement between A and B, to use this negativity, what you have to use is something called partial transpose, which is defined in this slide. Okay, so you have a bipartite system, two systems, and you transpose just one part of it. Okay, and then if the systems are entangled, then it can be proved that, it can be proved if the systems are not entangled, what we call separable, okay, then this partial transpose is still positive, which means that if it ends up to be negative, then the state must be entangled. Okay, so this is historical work by various people have early claims to it. They are in the bottom of the slide, and then the negativity is a measure, okay, which just adds up all these negative eigenvalues, the moduluses of them, okay, and then to make it one for two maximally entangled qubits, you kind of multiply by 2. Okay, so this is the measure that one we are going to use to quantify the entanglement between two blocks of spins. Okay. But before that, let me come a little bit to how one would measure this negativity. Okay, so if I've told you that negativity is this kind of thing, one has to be able to measure it in this kind of many-body system, and to measure something, it always helps to have a physical implementation in mind. And what we are looking at here are arrays of quantum dots, for example. So people are making larger and larger arrays. This slide is still a few years back, okay? And in these arrays of quantum dots, you can put one electron spin in each of them, okay? So there's one qubit in each of those sites, okay? So there are these things called quantum dot arrays, okay? And what is a nice measurement you can do here in quantum dot arrays? Okay, the one measurement you can do is, say you have a double dot, okay, and then one electron in each, and you tilt it. Okay, if there are singlet, okay, they can come to one dot, so you have a charge of 2 in this right dot. While if you have a triplet, okay, then you cannot come to the same dot, okay, because of the Pauli exclusion principle. So essentially you have a different charge configuration, right? And you do not actually need to do it like that. You can do it fast in oscillation. So you can read it in a radio frequency kind of way, whether you have a singlet or a triplet, in a double dot. Okay. So these are very good bona fide measurements. Now, if you have them, that's an interesting thing. This is the very simple thing that actually an exchange. So what you're doing when a singlet triplet measurement is actually you're measuring the exchange operator, sigma dot sigma. These are eigenstates of that. This is the variable you're measuring of two spins, sigma dot sigma. And that is nothing but the swap operator. So essentially you're measuring the swap operator. Okay, of 2 qubits. And this is all you need to measure these kind of entropic quantities. Okay, this is historically known from a long time ago that if you measure, if you can have few replicas of a system, say you had, so these are not in this slide, but if you had 2 replicas of a system, you could measure a nonlinear function of the density matrix, such as rho square, okay, trace of rho square. Okay, from that. Okay, so essentially what you have to do is you have to measure swap operators between identically construed replicas of the system. And the same kind of technique we found also works for negativity. Okay, for this, the earliest the smallest number of replicas you can take is 3. Okay. And then what you do is you measure the singlet triplet between, say, these 2 dots first and then these 2 dots. Okay, so essentially these are 3 replicas of the system. These are A, B, C as in previous slides. We want to at least find the negativity between A and B, where C is an environment. Okay, for example, then we will have these 3 replicas and we will measure the swap operator in one way. First these 2 and then these 2 in subsystem A, and subsystem B it's the other way around. Okay, so if you do that, then that's equivalent to measuring some partial transpose of a permutation operator. So this is partial transpose, means one of the sides have been measured in the other way. Okay, and then you can essentially get various moments of the partial transpose of the density matrix itself. Okay, you are measuring a partial transpose of a permutation operator, but you are ending up by this relation shown here in the middle, measuring actually the moments of the partial transpose of the density matrix. And it is from those partial transpose values that you can use things like machine learning to quickly hone in on the value of the negativity. Okay, so you can have just 3 moments, okay, to get quite a good accurate value. Okay, and this is being done for wide classes of states. Okay, volume law states and area law states of a collection of spins. You make 3 replicas and you can measure the negativity. Okay. Also during non-equilibrium dynamics, you can do these things. Okay, and the machine learning just with 3 copies gives quite a good construction of. So you first have to train with various moments the machine to come up with the negativity, and then it does it pretty well. Then much better than analytic techniques, which need far higher moments. Okay. Now, so if I've convinced you that some measurement is possible, I agree that if you are an experimentalist hearing this, you would not like to make 3 replicas to measure things, okay? And it is still on us to find out a good way to measure negativity from individual copies, okay? Of a many-body system, but that we don't yet have an answer to, but it should be ideal. It's just that the observables would be very complicated and many-body observables, but again, it should be possible to construct. Okay. Now, given this kind of negativity, what do we find? So this is now the entanglement. Now we are looking at the entanglement between 2 distant parts of a system with a gap in the middle. Okay, so this is like between faraway sides, and we are looking at lowest energy ground states. Okay, we know that these have less entanglement. Okay, these kinds of states, but they are easy to prepare, cool the system and stuff. At the same time, they have power law correlations. Okay, if they are a critical state, then they have correlations over very long distance. So one might naively expect that the entanglement will fall off as a power law. So there will be a lot of entanglement, in other words, between two distinct parts. Okay? But this naive intuition turns out to be wrong. Okay, so indeed, the mutual information, if you construct between two parts, okay, the total correlations, classical correlations, they do fall off as a power law. Okay? But the entanglement, as I said, is very monogamous. So this entity is entangled a lot also with the middle. So that means when you find out it's entanglement, it's a far away thing, there's a huge exponential loss according to the width of the middle. Okay, so this is why they kind of exponentially fall off. Okay, so what did we gain from this study, that this entanglement kind of exponentially falls off between two parts of a spin chain in, say, thermal equilibrium state or a ground state? Okay? Is the fact that you cannot extract much entanglement in this way, or if you want a quantity you can extract, this will be exponentially falling. Okay, and then this is true also for quantum field theories. Okay, because these kinds of chains are very good models of a quantum field theory. So you wanted to just know the entanglement between this region and this region. The total that is there itself is exponentially less. Whether you can extract by a mechanism is a different question, but it is exponentially falling off. Okay. Now one can also apply this negativity to when you have just dipped an impurity in a otherwise, say, free fermion system. It is very well known in physics that this creates a screening cloud. So a lot of free electrons effectively create an oppositely polarized spin to screen that impurity. Okay, and there's a length of the cloud. Okay, and then one can mathematically also estimate the length of this cloud through this negativity. Okay, that's an interesting point. So you compute the negativity of one impurity spin with a block of certain length, and you can show that that has the right kind of scaling of entanglement. Okay. Now, what you gain from that? Well, directly or indirectly. So what you gain from that is that you know that if you make, so this is of course a spin chain model of a Kondo system. Okay, this was earlier done by Affleck, and you can always map to semi-infinite line. Okay, so this is the idea here. So my internet was unstable for a moment. Was everything audible?
Yes, there was a bit of a, yeah, we did follow that there was some instability.
Okay,
but it was fine. Yeah,
okay, so now so we can take such extended singlets. So now what happens is you have an impurity spin which you have modeled by the spin at one end of a spin chain, and that has this stretched cloud like a collection of spins which is effectively behaving as the other qubit which is screening it. And by changing this coupling, you can make this arbitrarily long. So you can like have a stretched out arm, okay, with this spin. And then if you connect two such things, then you can have nice entanglement dynamics between the two end spins. Okay, so this is again like a bit like my previous part of the talk, okay, that you can actually establish with non-equilibrium dynamics now a maximally entangled state. If at a time t equal to 0, you do a quench, like you have a spin with its cloud, another spin with its cloud. At time t equal to 0, you just connect those two clouds end to end, and then you will get a very nice entanglement with time. Okay, it'll grow with time and fall. So you can probably use that to make quantum routers between distant qubits. So one qubit held in a dot and then a lead as its cloud, and then you will connect the leads suddenly, and these two dots should be entangled. Okay, mind you, this is not a super exchange, but if you had an effective super exchange between A and B through those clouds, then you would have to start with the pure state of the qubit and they would get entangled. Okay, here initially the qubits are completely mixed. They are screened with their cloud. Okay, so if you had a super exchange, that will never get rid of this mixedness. So this is not a super exchange mechanism, but it still achieves kind of entanglement. Now I will go to some a topic which is of very topical interest. Well, has been topical over the last 2 decades. Okay, so I think it started in 2007 or something, that people noticed this thing that even interacting systems can be localized if you have sufficiently strong, disorder. Okay, historically, it is known that for non-interacting systems, we are taking 1D here, that even a slight disorder completely makes it, localized. Okay. Now, so there was the open question whether this goes to interacting systems, because of course the interactions can serve as some extra energy to destroy the localization. And then what people found is, and I'm giving some numerical works that people have done, that the given sufficiently strong disorder, you can have, complete localization throughout the energy spectrum. Okay, so this is this vertical line here is the energy spectrum in terms of the energies of the system, and you see all these states in the purple are states which thermalize or ergodic. Okay, so they go to, they evolve to the whole space of possibilities of states, while the states in the left are localized. Okay, they retain good memory, and they are, in their individual states for a long time. Okay, and then the border is called a mobility edge. Okay. So now the question is, what can we learn from, this is a very extremely well-studied system by now, but what extra can we learn from using entanglement measures and entanglement-inspired quantities? Okay, first of all, a little bit more of history and some controversy which is there in the field. Is that, okay, so first of all, people are not very sure of the nature of this transition yet. Okay, but at least these 2 works and many other works tend to say that you can think of it as a second order phase transition with some scaling exponents. Okay, and there are mathematical proofs that if there's a scaling exponent, that has to be larger than 2. Okay, these are very general logics coming from a long past, actually, okay, of disordered systems. Unfortunately enough, when people did finite size scalings of various quantities, here this is a particular quantity which is the level repulsion, okay, which is characteristic of a of an ergodic system. Then people always find, people have done this with other things like von Neumann entropy and everything, you always find this nu equal to 1 instead of this 2. Okay, and here, so we thought, what can we do something about it? Okay, can entanglement measure help? But of course, one entanglement measure people had already looked at, which was the left-right entanglement, which is the von Neumann entropy, and that was still giving u equal to 1. Okay, which essentially means the verdict that the system was not approaching its true thermodynamic limits for the sizes that you could do. I should tell that these systems are not solvable analytically. Okay, people are always finding better and better numerical techniques, but if you use things like exact diagonalization, you are often restricted to smaller sizes. So people can always argue that you're not reaching its true thermodynamic values and limits. So we looked for something which is like a coarse-grained entanglement. So like the principal amount of entanglement in the system. Okay, is there at least like a EBIT of entanglement, like an effective single qubit of entanglement. So how you can do that? So that is not a bona fide entanglement measure, but what you can look at is called the Schmidt gap. Okay, if you have any quantum system, you can divide if it's as a whole a pure system, you can divide to left and right. It will be you will have these things called Schmidt coefficients. You can write it in this way in terms of these root lambdas, and then you can subtract the largest and the second largest Schmidt coefficient, and that is called the Schmidt gap. It kind of measures whether there's a unit of entanglement between the left and the right side. Okay, so what we thought is something like this, which is not the true complete detailed entanglement, but a very, rough amount, yes, there is entanglement or not kind of thing, that would probably scale better, because that would achieve that amount of time will already come with finite sizes. Then as you go to thermodynamic size, you will have finer and finer things. Okay. And that kind of intuition turned out to be right. So this is the Schmidt gap. So it is not particularly a quantum informational quantity, but it's a quantum information inspired quantity. And then you can see that its scaling is such that it does predict this nu, to be actually 2, okay, greater than 2. Okay, so greater than 2 is what is the verdict from earlier, disorder papers. So in other words, this quantity is already approaching its thermodynamic value, even for, as you see, the largest system size we have is 18, okay, but it's approaching its thermodynamic value because it's a quantity which achieves that value earlier. Then the more detailed corrections take time to achieve. So the entropy still does not achieve this, the total entanglement between left and right. And this is now the last part of the talk. Okay, so Urbasi, how much time do I have?
I would say around 5 minutes.
5 minutes. Okay, so that sounds fine. So we now investigated also with another quantum information inspired quantity. Okay, this is called so I'll come to that. First of all, one of the aspects of this many-body localization, and it might be immediately clear to you when you speak of the word localization, is that in an ergodic part, any local part of the system does not have memory. There's no local memory. Okay. Of course, in quantum mechanics, you cannot get rid of information as a whole, right? So the whole system always retains perfect memory. But if you take a subsystem, an ergodic system's definition is that very fast the information kind of delocalizes between very large parts of the system. So locally, the memory is gone. Okay. And on the other hand, if you have a very localized system, then what is happening is that you have gradually you have emergence of local regions where there is conservation and kind of things are kind of captured inside this, not going away very slowly over time. Okay, so there is a much more longer retention of memory. Okay. And we wanted to quantify the memory in a more concrete way, as one would do in terms of bits of information. Okay, as one would do in information theory. Okay, people have looked at it with various intuitive things. Okay, for example, correlation functions would become locked. These red ones are localized and blue ones are delocalized counterparts. Okay, so as you can see, there's also magnetization, like imbalances. If you start with the nil state, it almost remains the same nil state if you are in a localized state. Okay, then and people have looked also with entanglement entropies and stuff. However, these are not good enough to really capture the amount of memory in a subsystem in terms of numbers of bits. Okay, but because first of all, memory is a temporal correlation, between what you put in now in one box and in the same box how much you have at a later time, right? And that is what you want. On the other hand, these things, concurrence, quantum information, are more spatial things. Okay, so they are indicative of how much memory has gone from the local one, but they are not really quantifying how much is there still in terms of numbers of bits. And the thing is, quantum mechanical, you're allowed to do all sorts of measurements. Okay, so you can do an optimal measurement to extract the information. Okay, so that is not allowed necessarily built into all the measures that you're allowing to. So what is the main thing to use here then is what we call the Holevo quantity. Okay, this is a famous quantity used in quantum information for channel capacities. Okay, so we put in some information at a given site, at a given block in the many-body system. Okay, the rest of the spin chain is the environment. Okay, so that is like the channel, and this block of things is going from now to the future. Okay, so that the channel is to the future. So we compute the this is kind of a quantum counterpart of the mutual information. Okay, but it's in terms of classical bits. Okay, how many classical bits you put in in terms of quantum letters of the alphabet and how many classical bits you can take out by optimal measurement. So this is given by this whole-level quantity. So you send in the signal with various states rho k, and outcomes, you have to take a von Neumann entropy of averaged things and subtract von Neumann entropy of the individual ones, okay, to get really how much information you communicate. Okay? And so we computed this, and we also compared it with other things people have done before in context of many-word localization to access this memory. Okay, and this is what we find, that there is a nice hierarchy. Okay, so if you, for example, took this whole-level quantity, this is the second one, that is the true extent of the memory in the system. Okay, but if you just, because people have previously quantified von Neumann entropy, if you just took 1 minus von Neumann entropy, okay, then that kind of over quantifies the amount of information. Okay, so that would mean that there is some encoding which allows you to reach kind of maximum von Neumann entropy in the first part. Okay, but the environment of the rest of the spin chain may not allow it. So essentially, this part becomes 1. To get that bound. So it's an upper bound on the whole level, the best you can do if you're lucky with your rest of the channel. The environment is a natural spin chain dynamics, so it's not in your hand what it does. Okay? But the whole level is the correct memory thing. But if you take classical quantities, such as you take the mutual information, okay, that underqualifies, okay, because this classical mutual information is you're measuring only in one basis, okay, in a Z basis, for a computational basis. That's what experiments have done so far. They are things like they have measured imbalance, like you create a nil state and see how well it stays the nil state. Okay, that is like measuring in one basis. Okay, so if you do that, you get far less information, and then if you don't take a block and take one site, again you get far less information. Okay, of course these are all rescaled with the block size, so we have normalized this by the length of the block, so this is a fair comparison. Okay? So the whole level overachieves these classical things because there's some quantum coherence, and one can carefully say a 0, 1 could have gone into a 1, 0 in a superposition. So you should be able to read that out as well to get some bits. Okay. But what we found as a result of doing this recently is also something interesting, that if you deliberately, we then did the scaling of all these memory quantities, finite size scaling with whatever size of systems we had. What we found is if you deliberately decohered these systems, okay, then they are scaling exactly as this thermodynamics would dictate. Okay, so for example, we first found that this whole level quantity, when you took its decohered counterpart, the classical mutual information, it of course under quantifies the information, but it has better scaling with a higher nu. So inspired by this, we took this von Neumann entropy and decohered it, and this is like the classical Shannon entropy. That actually scales exactly like this with this nu greater than nu equal to 2, which is called the Harris bound. Okay, so essentially the message is that you can consider a thermodynamic limit like the rest of the system just by dephasing the quantities. Okay, which makes good intuitive sense. Yeah, the dephasing is still on. Okay, when the system is still going large, and that means that you can do thermodynamic limit studies by deliberately dephasing quantities, okay, which is useful both theoretically and experimentally. In theoretical analysis, we see that in the transition regime, very quickly, if you decohere both the things approach each other with length. Okay, in many-body localized regime, the coherent and incoherent approach very slowly with length because the dephasing is also slower but still happening. But nonetheless, they're going closer and closer. Okay. However, this dephasing is happening essentially from the interactions. So if you switch off interactions and had free fermion models, then they would never come close, the whole level and the dephased counterparts. Yeah. So this kind of message which arises comes out from measuring these memory quantifiers. So this is the end of the talk. I would like to say again, just put up this slide that what I have said to summarize. I have shown, I've been very fast probably, but just to give you a flavor that that spin chains can be used as quantum channels, sources of entanglement, makers of gates, and perhaps some rudimentary algorithm like the search that we spoke about. And also that if you apply quantum information tools to spin chains, you can sometimes get useful messages out of it. You can probably get these messages out by different quantities in different ways as well. But nonetheless, the quantum information route helped us to reach there. Okay. So yeah, so that is how I would like to conclude. Okay. And maybe I can take a few questions. Thank you.
Thank you very much for this very nice, very comprehensive talk. So yeah, so the floor is open for questions. We don't have any in the chat, but if someone wants to just unmute and ask, that should be fine. I think
Shogata, this is Aninda here, so
yes.
Maybe I can ask a question. It was hi. So this was a very interesting talk. I had a question regarding one of the first, maybe the middle part of your talk, where you were where you showed that when you turn on this, when you modify this nearest neighbor coupling, your alpha changed to 3/2 for
right.
Yeah. So I would have thought that if you make the coupling more local, then you should recover at least the entanglement entropy. There should be some signature for this log scaling that happens in one-dimensional CFTs.
Right.
Do you get a transition from this log scaling to something else as you make the interaction non-local?
Right. So that is not a problem we have studied. Others may have studied it. Okay, but I mean, we were about to study something like that in context of in context of many-body localization, but we found there's a lot of literature on that. Okay, so there would be something like that that it would probably go from a volume law to an area. The log L. We still call it an area law.
That's common.
Of course, when you get more distant, so definitely when alpha is 0, that you're any distant, then you would have a volume law.
Yes.
And that is an interesting problem, but I think there is some literature on that. Our work here was much more at a much more mundane level, I would say, because here we have a single excitation hopping. You see, so the single excitation is initially superposed between all sites. Okay, and then it concentrates on the marked site, and that also depends on the range of the interaction. Okay, we are doing this partially inspired by ion traps, because in ion traps, by making more tight, you get a very long range interaction. Okay, and when you really make them very loose, like you make a more and more length scale, then eventually it becomes like a dipole coupling 1/r³. Because the phonons are just so you give a mass to the phonons, or you kind of try to make the phonons massless, you get 1/r³.
Right.
So what we are finding is at 1.5 somehow this advantage is going away.
And this, if you plotted this graph against some entanglement quantity on the x-axis, presumably, I don't know. So if the entanglement scales like volume as opposed to area, will the entanglement be more or less? Presumably, the question is not very well defined because the answer is infinite anyway. So you have to have some regulator in place.
Right. But, some kind of lattice scale A. You have, and no, I think as I said, this is an interesting question. So maybe the 1.5 we think, I mean, Dylan, who is in the audience, may even know that there's probably a paper which says that 1.5 is something like that happens in 1.5. Okay, that it may go from volume law to area law, but I'm not very sure. I can look at, there is some literature in that, and we were quite
Okay.
interested in that, but we haven't done it because we saw that there's been already a lot of work in that.
Okay, thank you.
Yeah.
Can I ask a question?
Yes, please.
Shogata, yeah. So that was where you discussed this determination of negativity using those replicas and machine learning, that slide. So when you talk about replicas, so in that protocol, how do you, is there any self-testing that whether there, how do you test whether it is a replica or not? Means replica, how do you define replica?
Okay. So we assumed at least initially that these are exactly the same states. Okay,
replica that are produced means they are prepared. The preparation.
Yeah, the preparation.
So it's ideal kind of thing.
Like IID, whatever people call. Yeah, so identically prepared system. I understand that for a many body system that may not be in practice.
How sensitive it is to the departure from them and those kind of questions, unless you put something, the reliability of such a way of doing, unless it is computed quantitatively.
I think there might be something in our paper on this slight disorder, but if it is not there, I think it's an important question to check that.
And also machine learning, you use the machine learning that number 3 comes because the machine takes finite time, or what?
No, three with just 3 replicas like this. Okay. So we are computing this rho transpose cubed or partial transpose cubed. That moment we are considering trace of partial transpose.
Compute it using 2 also. Means you have computed with 3.
No, so 3 is so for 2 there is no difference between an order.
Okay.
So 3 is the minimum.
Okay.
This partial transposition makes sense because you have to have opposite order in the 2 parts, and then that kind of suffices for a good modeling of the negativity. Okay, of course you can do the negativity with more replicas also.
And when you said the machine can recognize it, means you take the help of machine.
Yeah, we are training it with many partial transposed moments.
Okay.
And the output comes the negativity. It's a nonlinear function, so that's why the machine learns it.
And the other question is in the last part of your talk where you talk about the memory and you use the Holevo quantity. You define a cut between the environment, what you consider to be environment, and what you that portion. Can you explain a bit?
Okay. So I was fast here, I guess.
Yes.
So we take a spin chain here. I've drawn it as a circle, like a periodic boundary condition. It need not be, but then you put in something. Okay, and the rest of the thing is the environment. So you take a block in which
you put in something and the rest environment. That means that you do some.
Okay, so I'll tell a bit.
Just tell us slightly more.
Right. So these things, these many body localizations, as I said, is a full spectrum thing. So the localization is across all energy states. It's not just the lowest energy. Ground state is often quite localized area law anyway. Okay, but with disorder, so mid spectrum states typically are very thermal or ergodic of any system, because you're not trying to minimize the energy of closest local physics. Okay, so on the other hand, if you then put in disorder in different sites, they become localized, as been said here. So we are taking mid-spectrum states here. So first of all, we are selecting as an environment, we are diagonalizing the system and selecting a mid-spectrum state.
Okay, that is.
And that is our environment. Okay, then we are averaging over a lot of varieties of environments.
Okay, I understand.
And then we are a string like 1 0 1 0 or all zeros to all ones in this block. Okay. we are literally not putting in all message states that one could, because that actually then changes the temperature a little bit as well. We are kind of staying in the mid spectrum, and then for all those message states evolves to some complicated final states during the evolution, open system evolution, so that the final information you can get is you have to subtract the von Neumann entropy, which would come from mixing those message states. From that, you have to subtract the individual mixedness of the states. Yeah, that's the whole level.
And that is why the whole level quantity is.
Yeah. So this is the best accessible information indeed from the system. If you vary over all POVMs, all kind of best operations, you can do.
Okay, any further questions, comments? So what is the experimental status of, this sort of work? So,
okay. Yeah. So experimental status is, so we would like to take it to more directions. So, one of the things we are working with various colleagues are quantum dot arrays.
You showed that slide with those, this 3D.
So we would, of course, these wouldn't immediately scale to very large things. Okay,
right.
and with quantum dot arrays, people have done things like quantum state transfer recently. Yes. Some US groups. Okay, so we are mostly working with Charles Smith in Cambridge.
Yes.
And then, so that is solid state implementation. Now, in Josephson junction arrays, people have done pretty much similar things already. Maybe in other language like quantum walks and stuff. But there is some literature, and then people have implemented these things in these new quantum computers, for very few qubits and stuff. And we have done something in photonics also with this the block entropy thing, this up down and down up down up to Maxwellian tangles, and that was with Fabio's group quite a few years ago. We did something. So this can be but those would be like simulated fermions. 2 photons in HV minus V8 state, then we think of H and V as pseudo labels rather than real labels. Then they're spatially they are like fermions, and then we
so you can mimic it and do a proof of principle.
And did that kind of thing.
Right.
But ideally, I would like to the first part, the state transfers or different gates or algorithm, I would like them to be useful in some quantum computing application. That is probably not yet used. So people still use microwave buses or photonic buses. So my hope is for these things to be more useful for exchange coupled spins kind of things.
Is there any trade-off because of the perhaps the literature regarding the decoherence in the systems is not as populated perhaps as of now? So maybe that is why, excuse me, there is less usage in practical systems. So that would be an open system, open area to enrich in some sense.
No, obviously. So the decoherence
excuse me,
is the problem. So one has to think whether but if these things would have hopefully be so the idea would be to do many transfers and do some kind of entanglement distillation after that, the registers. So so it's just a quantum channel is not necessarily, so decoherence might make it worse channel.
Right.
The typical tendency in quantum computing is to use super exchange like things. Okay, so where the mediator is eliminated, all but eliminated. So mediator is completely virtual. Okay,
Okay.
so so its thermality or its decoherence becomes immaterial.
Immaterial.
And then the gates are very high fidelity. But of course, whenever you are using virtual transitions, it's very slow, because your couplings have to be much less than the minimum gap in the system. Okay, so essentially this is so I mean, these things are fast, the things I was talking about. On the other side, I think we need quantum simulators to do the entanglement measurements and stuff. Also have not yet been done, this kind of using replicas to measure entanglement. Has been, okay, so there has been, people have measured von Neumann entropy using two replicas in optical lattices.
Right.
So yeah, so the net answer is the experimental status is probably not as good as I would have hoped for, and we have to ourselves work for that.
Surely that means there's a lot of scope for
we haven't
doing
done enough effort probably on that yet. That's the thing.
I think Dylan has provided an answer
Okay.
to Anindo regarding his question.
Okay, okay.
Yeah, I mean, in some sense, he says, I don't know the answer to your question, and then he gives a lot of detail about stuff. So, Anindo,
I see.
please have a look.
The papers, yeah.
So, Shashi, had you raised hand, or was it a mistake?
No, I did.
Oh, is that Mahesh then?
No, I was.
Oh, okay. Did you want to ask?
Yeah, yeah. Thanks. Thanks, Professor Bose, for this nice overview. Actually, I was having some trouble in understanding that how should I interpret the entanglement between like pre-fermionic language, because for spins I can understand that how to, I mean, this spin and that spin is entangled, and so let's say concurrence, or for that matter negativity. But how should I understand the entanglement between in the language of pre-fermion? Is it entanglement between two sites, or is it
yeah, so you know, so we mark things as modes in a classical way, right? We say that this box or this momenta is our mode we are considering. Okay, like for an electron, a mobile electron, or for a mobile photon, this momentum direction is our mode, or that momentum direction is our mode. That is the marker. Okay, so for free fermions, if the fermion is sitting here, we would call it fermion A. If it is sitting there, we would call it fermion B, and then we can look at the entanglement of the state. Okay. However, there is one important aspect in case. So in this sense, it's a good question. If a fermion was just delocalized between two sites, it's a single fermion and you have two sites, it's here or there, okay? One should not ideally call it like a occupancy-wise, say 0, 1 plus 1, 0 kind of entangled state, because you can never use this really as a resource, because you cannot superpose a single fermion with no fermion, okay? Because there's a fermion superselection, so fermions are always in pairs, okay? In all physical processes, they're always created and destroyed in pairs. So you cannot really superpose, like if this was a photon, you could interpret it, though again difficult to experiment with, as an entangled state. Photon here, no photon there, photon here, no photon there. But then you have to supply it with external lasers to do some operation. If it was a bosonic atom, you could still do it, to supply with external BECs. But for fermions, you cannot really superpose no fermion and one fermion. You can superpose no fermions and two fermions and four fermions and like that. Okay, so this is why when you label the modes, spatial modes or momentum modes for entanglement, you have to be, when you have fermions, you have to be careful that you are not superposing an odd number of fermions with the even number of fermions. Okay, then you can legitimately talk about entanglement, because entanglement is all about being able to change the basis locally. So have correlations between varied bases right? So you have to be able to superpose 0 and 1 locally, okay? And that is not possible for a fermion. But otherwise, it's same thing, whether fermion or bosons. You just define the modes and you label the things according to the modes. Then they become particle in that mode, particle in this mode, and you can quantify the entanglement.
So I think we will treat that as the last question then, Professor Bose. So thank you very much once again. It was very nice listening to you today, and I hope people go back with lots of questions in their mind and lots of food for thought. So thank you very much. Yes, stop the recording.
Bye.
Bye. Bye.